All right, back from break. Let's pick up where we left off. And so here is that Planck distribution formula, and it looks just terrifying, I think. And so let's go back and see if we can find out a picture of that function. There we go. There is that Planck distribution. Here's some sketches. Okay, going back and looking at the stuff that we looked at in the earlier portion of the lecture, that's what these Planck distribution formulas look like in terms of wavelength. And there it is. And then what Planck did was he took this formula and he plugged a bunch of numbers in. He tried different values of h, the constant that he came up with. And so I had to add in over here. Think of this, he's using paper, pencils, a slide rule, and graph paper probably. So just using it, no calculators, but taking this formula and carrying out the calculations over and over and over and over to come up with a value for h. And when he did that, he was able to, I don't know at what level of precision at that time, but the current accepted value for Planck's constant is 6.626 something 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 10 to the minus 34 joules times seconds. And this is considered to be the fundamental constant of quantum mechanics. This tells us how the wave properties, the interference properties of particles are related to their energy and momentum. Particles have a certain energy and momentum, and that will tell us what their frequencies and wave numbers are. So, very important number. And it's Planck's. This is Planck's constant. He came up with it. So again, here's a reminder of what's going on now. If I come back to this slide, and here's what I was going to warn you guys about. This tells me that this function is the intensity already, and that's not really true. It's the intensity per wavelength. And so what I wanted to do was change that. So I wrote this as a function of wavelength. Now, temperature is in there also because, as we saw, as the temperature changes, this distribution will shift. So we could include temperature, but when we're carrying out calculations, we're typically thinking of temperature as a constant. And we're integrating, when we carry out integrations such as this, we're really just integrating over the wavelengths, not over temperatures. So there's some fixed temperature at which we're looking at this distribution. Temperature tends to be treated as a constant. Now, wavelength is not the only way we could represent this distribution. This could be represented in terms of wavelength. As you've seen, in some cases, they're representing it in terms of frequency. We can also represent this in terms of energy of the photons. So we can also represent this as some amount of energy, the horizontal axis as a varying energy of the photons, and no surprise, that's my favorite way of representing these. Again, energy conservation is such an important feature within physics. We use energy conservation in so many different types of problem solving that working from energy among all the particles as a fundamental property usually is the best way to get a good understanding as to how things are related. So let's go back and look at this sunlight example again. The sun is at a temperature of 5,800 kelvins. If we put in 5,800 kelvins, the peak intensity was at 500 nanometers, if you remember. But what happens if we look at 600 nanometers? So rather than looking at a point right at the peak, what if we shift a ways over? Well, if I go in and I integrate across all possible wavelengths, We know how to do that. That's sigma times t to the fourth, and that gave us the 64 million watts per square meter. So that would be the total area under that curve. What we would be doing is taking the function, the intensity per wavelength function, and integrating it. Now that function, it's not I, it's di d lambda. And so that's where I have issue with the textbook. What they're calling I is actually di d lambda. It's not I. You can't integrate I and get I back again. What you do is you integrate di d lambda over lambda, and what you're doing is you're adding up all of the di's. So when you add up all the contributions, the little di's, they're going to add up to the total intensity. So that's how this works. So to get the intensity, we're going to add up all the little di's, and that means adding together this function and integrating it over the wavelength. And we'll see how that's done. But right now what I want to do is take this function that we've defined, this one right here, and say, let's look at one particular wavelength. Let's look at a wavelength of 600 nanometers. Okay, it's garbage day. What can I say? We're looking at 600, you can hear the garbage trucks, 600 nanometers for the wavelength. What is the particular intensity of light at 600 nanometers? Now what I did then is I plugged into that formula. I plugged in my factors of h and my factors of c squared. I plugged in wavelengths to the fifth power, and I plugged in all that hc over lambda kt stuff, where k is Boltzmann's constant, and I plugged in 1500 kelvins. And what I'm doing is I'm solving for the value of that function at the wavelength of 600, and it worked out to be 7.79 10 to the 13th watts per square meter per nanometer, per meter. And then what I did was I wanted to work in terms of wavelengths of nanometers. So what I want to do is I want to compare what's the intensity at 600 nanometers, what's the intensity at 601, 602, 603. So if I assign these bins, these d lambdas, and if I set each one of those d lambdas to be 1 nanometer, that's a good way of breaking up the function. 1 nanometer is a small enough width that conceptually I can think about following that function and not introducing much of an error if I think of that in terms of 1 nanometer wide bins. So that's what I did, and for this particular wavelength I ended up with 77,880 watts per square meter per nanometer of wavelength. So it's got that extra per nanometer of wavelength in the units. If I moved on to 601, this would change a little bit. And so we could go through one wavelength at a time and calculate just how much intensity is coming from that wavelength. If I wanted to get the combined wavelengths, I could, probably not the most efficient way, but I could take that list that I had calculated. So we could take this formula. This would be something good to program, right? Because you don't want to carry out hundreds and hundreds of these calculations, which Planck probably did. Hundreds and hundreds of these calculations. You could program something, your electronic device. I could program my calculator, and so it would give me a list, or I could, program in Python or whatever, and produce for each wavelength what's the intensity. We could add together that column of intensities, and we would have the overall intensity recovered. We would be able to go back and recover this value by adding together all of the individual intensities one wavelength at a time. That's the idea. So just thinking through, imagining doing that is a good way to build up conceptual understanding about what do we mean when we're carrying out that integration, and what do we mean by an intensity function per nanometer. All right. Here is that function again. We just can't get rid of it. What I wanted to do now is take a look and see. There's actually a homework problem that asks you to do this. I was kind of curious. How would we find out where the peak wavelength is? How would we come up with Wien's law? Wien's law seems to work. Why is that? Can we show that mathematically? Now, you guys have been taking calculus classes long enough. You know that what we can do is take a function, take its derivative, set the derivative equal to 0, and find out at what value of lambda this function levels off. That would allow us to find the maxima and the minima, and we're after a maxima, and that approach would work. Now, we could directly take a derivative of that, that's not a problem, but there's 5 powers of lambda here, and there's a lambda, an inverted lambda, inside an exponential, and I was thinking maybe there's an easier way we could do this. So I did a variable substitution. Instead of using lambda, what I did was I took everything in the argument of the exponential. Now this is a standard technique. If we look at an exponential function like this in physics, there could be a lot of stuff going on. And in this example, it was hc over lambda kt. Well, what if we took a variable substitution? I'm going to call it x. U is another one of my favorites, but for this I used x. Is equal to hc over lambda kt. What that does for us is it simplifies taking the derivatives of my exponential. Now, taking derivatives of the exponential is kind of trivial because a derivative of e to the x with respect to x is e to the x. And the other feature for us as physicists or as engineers is x is unitless. I am guaranteed, you know, in math classes, you very seldom are forced to deal with units, but in physics, every problem has units. I know that if I look at that combination hc lambda to the kt, it can't have any units because I'm exponentiating it. That can't have units. It's like cosines and sines. They can't have units if I'm taking the sine or a cosine. Radians are the unitless unit, right? So anyway, this idea of using a variable substitution with some variable that's unitless actually is kind of handy. Because when I look at formulas involving x, and you can see that's where we're headed, I know that the x itself doesn't carry any units. It's an easy way to do unit analysis as I go through the derivation. So what I did was I took that statement of my new variable, I flipped it around and solved for lambda, and then I solved for 1 over lambda, because see where the lambdas, that's 1 over lambda, and that's 1 over lambda. And I got this new function, I called it g, because g comes after f. And when I'm defining functions, the first thing I think of is f, and if I've used f, the next thing I think of is g. So I said, let's define a new function, which is that function, with this new variable substituted in everywhere. It came out to be a bunch of constants. See all those constants? And then it turned out to be x to the 5th. Now that's because it was lambda to the 5th in the denominator. The way we made the definition, now we have x to the 5th in the numerator, and then ex to the minus 1. And this had the feature of when I took the derivative, I got to use the quotient rule again. I love using the quotient rule. So bottom times derivative of the top minus the top times the derivative of the bottom over the bottom squared. Now we're going to set that whole thing equal to 0. And that says that all the constants out front, I don't have to pay attention, okay? Because the constants are not going to be involved in giving me a 0. So now I can just focus in here and I can ignore the denominator. I really just need to get that numerator to go to 0. So that's what I set. I said e to the x minus 1, 5x to the 4th is equal to x to the 5th times e to the x. I moved some stuff around, maybe not in the most efficient manner, but eventually I got to this. Now this turned out to be useful because that was easy to program into my calculator, And my calculator has a successive approximation program built into it. So I can give it a function and tell it to search for a value of x that satisfies that formula. Now, you might be thinking, well, why didn't you do a few more lines and just solve it? And that's because you can't. Okay, I hope you guys have seen in your math classes, there are what are called transcendental equations. And transcendental equations can't be solved in closed format. There's no way I can take that equation and solve it by saying x equals, because I have an exponential on one side and I have powers of x on the other. And anyway, so I program my calculator and it says the solution to that, the conditions such that we get the function hits a peak, is to set x equal to 4.9651. I kept that many sig figs. So that's just a numerical solution to this condition. And I plugged that back into my wavelength formula. And I rewrote this as lambda times t because that's what Wien's law looks like. Here's Wien's law right there. Here is this Planck distribution. And so I isolated everything that corresponds to the constant A. I go, okay, the constant A actually is h times c over Boltzmann's constant divided by that, 4.9651. Well, that's kind of interesting, kind of fun, that this physical constant that experimentalists first developed actually has a theoretical explanation to it. And it's not just a bunch of, standard physical constants. It's also got this number in it, 4.9651, which is the solution to that equation that maximizes the function. All right, plugging everything in here, no big surprise, I hope. This is 2.90, 10 to the minus 3 meters kelvins, so that's it. So Wien's law is no longer just an experimental observation. We now have a theoretical understanding of where that's coming from. We can start with the Planck distribution and derive Wien's law. Ooh, what if we started from the Planck distribution and derived not just Wien's law, but what if we were to derive the temperature to the fourth power formula? So let's do this. Same idea. I've got the Planck distribution in terms of wavelength, but I'm starting to like this Planck's distribution in terms of x. I think that was a really handy Planck's distribution formula. So what we're going to do this time, instead of maximizing that function, is what we're going to do is take the Planck distribution, the function of lambda, and make the same substitution as before. Now, what I want to point out here is x we wrote in terms of wavelength, but probably even a more important connection is that if you remember, hc over lambda is equivalent to the energy of the photon. So it turns out that this x variable that we introduced is directly proportional to photon energy. And I was saying photon energy is kind of the best way to think about this. Now, the reason x is dimensionless is because it's not just energy, it's energy divided by kT. But you guys are thinking, oh, I'm fine with that because I took physics 4B and I did thermodynamics, and every time we had an internal energy or an average energy of molecules, it was always in terms of kT, right? So what I'm doing is I'm starting to think, these photons are starting to look more and more like atoms and molecules. Photons are particles of light. If I looked at a collection of atoms and molecules, I could come up with a distribution of molecular energies. In fact, we did that in Physics 4B. We called it the Maxwell-Boltzmann distribution. It's back in chapter 18 on kinetic theory. So a collection of gas molecules has a range of different energies. So does a collection of photons. So if I have an object radiating all these photons, there's a particular distribution of energies, and X is actually a way of keeping track of how much energy the photons have. All right, so it's a pretty nice feature that we can think of it that way. So we did the same substitutions. Now what's different this time around is that before I was just looking at the function itself and where does it maximize. But to calculate the total intensity of all the light across all possible wavelengths, across all possible photon energies, this is integrating across wavelengths, this is integrating across photon energy, I have to carry out an integration. And that means that I also have to determine d lambda and find out how I'm going to replace that with dx. I can't work in wavelength increments anymore. I got to work in energy increments or increments of this variable x. So in addition to changing the function, I also solved for d lambda. Now d lambda, coming from here, worked out to be hc over kt dx over x squared. There's a minus sign there. Now, I can look at these integrations and say, you know, why am I getting a minus sign? The intensity is not going to be negative, is it? And what that minus sign with this variable substitution, and maybe you've seen this in calculus, when I get a minus sign here, it's equivalent to telling me that I'm reversing the direction of integration. Before, and let's think about this, I was integrating from short wavelength to long wavelength. But when I integrate in terms of energy, I'm integrating from low energy to large energy. That's the reverse. Because the low wavelength end of the spectrum corresponds to the high energy end. So it's like doing this. It's like taking all these bins of wavelength, right, and cutting them out and reversing their order. So I'm going to get all these bins of energy compared with these bins in terms of photon wavelength, but the bins are going to be integrated in the reverse order. So I can ignore that minus sign because I do intend to integrate from low energy to high energy. Okay, so that's nice. We justified dropping one of our minus signs. All right, so here we go. If I take the function of lambda, d lambda, and I follow these substitution rules and put everything in terms of x's, this is what that function looks like. So I've come up with the equivalent expression for gx dx given f lambda d lambda, and this is what we end up with. So I had 2 factors of x here. I had 5 factors of x here. Those are going to cancel down to 3 factors of x. So I'm going to carry out this integration, this one right here, and I'm getting a gx dx. Here's a bunch of constants. Look what happened. I ended up with, okay, there is a 4 right there. So, which I've got to get added to. So that's like 3 items I got to take care of, for today. So there's a 4 right there. And I'll put that back in, or you guys can draw that in. What I'm left with is this. Once I've brought out all the physical constants, what I'm left with is an integration in terms of x. Now that's x to the third over e to the x minus 1, integrated from 0 to infinity dx. Now I can carry out that integration, and that's fine. But even before I carry out the integration, I can already say that in some sense the problem has already been solved. Because this integration has no temperature dependence in it. This is just a number. When I carry out this integration, it's just going to give me a number with no units because x doesn't carry any units. And these sorts of calculations, again in physics and engineering, are fairly common where we kind of push everything with units, or we bring everything with units out of the integration in a way where the integral is left with just numbers. And so that's just some kind of a factor that has to be determined. Kind of all the physical importance is out here in the constants. And what we can see is that if we, what we can recognize is this is t to the fourth power, and that I can now identify where sigma is. The Stefan-Boltzmann constant consists of everything except for the t to the fourth. So sigma, the Stefan-Boltzmann constant, would be 2 pi hc squared, Boltzmann's over hc to the fourth power, times that integration. The only thing we've left out is t to the fourth. Okay, so again, this is the distribution in terms of x, which is directly proportional to energy. The formula that we have for combined integrated intensity across all possible photon energies gave us this expression. It turns out that this actually is pi to the fourth over 15. I don't know how you would do that. I would have to go back and find some tutorial to tell me how to do that. But numerically, that's 6.494. So when we plug that number into all of this other stuff, we end up with Stefan-Boltzmann constant that's 5.67 10 to the minus 8th. It worked. So we got the Wien's law constant, and now we're getting the intensity temperature constant, the Stefan-Boltzmann constant. And now we know what it consists of. It consists of all these other constants multiplied. It's a lot of stuff, right, that includes. Okay, so let's try this. Now, what we had shown in this previous slide, the one right here, was that we could now use x as a variable to keep track of our photons, and that in some sense, x was keeping track of photon energy. X is directly proportional to energy. Now, the pattern of x's changes if the temperature changes, but for any given temperature, x represents a certain amount of energy. So we can take that distribution and we can divide it up. Let's do this. Let's take sunlight. We've looked at sunlight a few times now. Let's go in and say, look, sunlight looks something, this distribution in terms of, oh my gosh, I put f of x. Remember, that's g sub x. Ooh, and that's g sub x, and that's g sub x, and that's g sub x. Yeah, see, I drifted back towards f. That's what always happened with every function I define. If we say this is now, I'm going to go ahead and say, let's just call it f of x. So if we do this function in terms of this variable x, the one that we defined on the previous pages, what we could do is go, okay, for sunlight, we're evaluating x at a temperature of 5800 kelvins. If I take the boundaries of visible light we've been saying runs from 400 to 700 nanometers, I can convert that to energy. So we're kind of through with the 400 to 700 nanometer stuff. I want to start thinking of visible light consists of those photons with energies between 1.77 and 3.10 eV. When photons of visible light hit my retina and they activate my retina and I experience seeing something, having vision, the molecules in my retina are thinking in terms of this. The photoreceptor cells are thinking in terms of the energies of the photons coming in. That's what boosts them from a lower quantum state into a higher energy quantum state. They're not thinking in terms of wavelengths. My retina is thinking in terms of photon energy, of the particles of light that are coming in and reaching the rhodopsin proteins and the, what's vitamin A? Molecules inside my rhodopsin proteins inside my photoreceptors. Anyway, they're thinking in terms of energy per photon. So I used our formula, right, of x and determined that, well, the visible light at a temperature of 5800 Kelvin corresponds to X values between 3.54 and 6.20. So I could do a plot. What I found out was that 3.54 and 6.20 show up over here on that side of the Planck distribution, given in terms of X. Now, this entire integration, remember, this was the intensity formula right here. With this to the fourth power, okay, boy, chapter 37 has been a challenge, huh? Okay, I guess I gotta proofread one more time. So there's a factor of 4 right there that you guys, I mean a power of 4, you guys see that. And then this integration right here is 6.494. What I did was I subdivided this integration. I integrated, first of all, from x equals 0 to 3.54. Now that's going to give me all the bins of that function that correspond to the infrared part of the spectrum. So by doing 0 to 3.54, I ended up with 3.30. Now that's compared with a total integration of 6.495. That's 51% of the integration of the intensity. So even though the sun clearly is bright, it lights up, it generates a lot of visible light, about half the energy, maybe a little bit more, 51%, is coming off in the infrared part of the spectrum at energies, photon energies below 1.77 eV. The next part that I looked at was the visible part. I integrated between these. Now, when I say I integrated between this, I programmed that function in my calculator, I told it the limits of integration, and my calculator responded. So my calculator went and carefully integrated this, 2.39. Now that's a fraction of this total number, and it's 37% of that. So it said 37% of the intensity of the light, 37% of the energy, is coming out in photons between 1.77 eV and 3.10 eV, and that's the range of photons that my retina recognizes. So my photoreceptor cells respond to those photon energies. 37% is going to be in the visible part. Now, how much of that dangerous UV is being generated by the sun? And when I looked at the rest of the expression, those with X values above and beyond 6.20, that worked out to be 12%. So, kind of interesting. Sunlight, 51% infrared, 37% of the energy is in the visible, 12% of the energy is coming in as ultraviolet. Now there's going to be little bits of X-ray and there's going to be bits of microwave and such, but the infrared and ultraviolet regions are so broad that to a very good approximation, this upper region is going to be ultraviolet. The X-ray port, going to be really, really, really tiny. So that's pretty cool. We can take sunlight. This is our example with thermal radiation. We can take sunlight and break it up into different portions of the electromagnetic spectrum, into visible and such. Now, I actually went in and graphed this. So I went online to my favorite graphing website, and here is the Planck distribution in terms of photon energies, and here is that function plotted. So this is the function that I plotted here. Now I think I got this wrong. That's supposed to be 6.2. This is 3.56, something like that. Anyway, that's a more carefully drawn breakdown of the infrared, visible, and UV, and I think that is supposed to be 6.2. It needs to be shifted just a little bit, not much, but that's a more carefully drawn function to see what it actually looks like. And notice that the peak photon energy occurs at an X value of 2.82. Okay, so the peak energy of a photon isn't the same as the peak wavelength because the bins are not the same size. That's kind of interesting that if we plot this in terms of wavelength, there's a particular wavelength at which the intensity peaks. If we plot it in terms of photon energy, there's a particular photon energy at which it peaks, but those two don't match because of the way the binning is done, the way that the vertical regions are divided up. All right, and now I just want to come back and kind of emphasize this point one more time. What the Planck distribution did was took light and said, hey, it's made out of photons, and I can think of the distribution of photons as kind of a random set of energies. Well, not random, but following a particular distribution, the same as a bunch of gas molecules. Back in chapter 18, we did dNdE calculations there and got this graph. The Planck distribution, we get something that's not identical, but it's similar. And probably by the time we're through this chapter, 37, and into chapter 38, we'll see. We may come back and do a more careful derivation and comparison, kind of a side-by-side. What's different in deriving formulas to represent the energies of gas molecules compared with derivations of energies of photons. Okay, and you'll see there's some real similarities in terms of available quantum states and what's the most likely, statistically most likely way the photons would divide up. Let's move on to another topic. So that first topic, the thermal equilibrium, or the thermal radiation, I think is a really important topic, a lot of interesting stuff, but it gets pretty difficult, right, carrying out all those calculations. Let's do something easy. So this is the easy sections in the chapter. All right, this is what students often ask for on the midterm problems. But let's take a look at, here we have a light source. Here we have a photocell. Now a photocell says it's like a vacuum tube. So I got a glass tube and it's got a couple of electrodes inside, a couple of pieces of metal. In this drawing, one of these is kind of a post, and this one is a curved, and the phototubes we have, we're going to be using these in a Planck's constant, what a coincidence, lab that we're going to be doing here in a couple weeks. So when we do the Planck's constant lab, we're going to be looking at the photoelectric effect, and our phototubes have a curved surface inside, and what we do is we shine light on this kind of stretched out curved metal surface, and if the photon energies are large enough, they can dislodge electrons. And so it's called the photoelectric effect. Photons of light come in, and if they have enough energy, they can overcome the binding energy of the individual electrons, and we can generate a current that way. So that's what's going on here. Here's the ammeter getting to measure that current. Now in this setup, the battery is set up, it seems the battery is set up to try and push the electrons this way. So there is a voltage encouraging the electrons, and that means the photons don't necessarily have to have really high energy. The battery's trying to help out. In our labs, we actually turn the battery, and in standard setups like this, you usually turn the batteries the other way to try and prevent the electrons from being able to cross, but this one's giving them a boost. We'll talk more about that when we do the lab. All right, the idea works something like this. The photoelectric effect was again something that researchers were observing back in the 1890s or whatever. This had been experimentally observed, and researchers were trying to figure out, why is this happening? So the idea that Einstein came up with, once Planck had developed or introduced this idea of light having kind of fundamental units of light, And Einstein kind of jumped on this and goes, look, it's just particles. Light's made out of particles. Well, Einstein moved on and applied this to the photoelectric effect and was able to show, explain how the photoelectric effect worked. And in fact, when Einstein received his Nobel Prize in Physics, he also got a Nobel Prize in Peace. His Nobel Prize in Physics, surprisingly enough, was for the photoelectric effect and didn't really involve special or general relativity. And special and general relativity are kind of the most remarkable developments ever, maybe, of individuals. In any case, Einstein came up with this idea that, hey, lights just consist of photons, and each photon has a definite energy to it. So some of the photons will have more energy, some of the photons will have less energy. But if a photon comes in and reacts, if a photon comes in and hits something, its energy will determine what the options are. If the photon comes in with not so much energy, it could be absorbed. If the photon comes in with more energy, like in this example, the photon could end up dislodging an electron. An electron could be separated from the material. So let's see. Yeah, so the idea with the photoelectric effect is as long as the light source consists of individual photons that have a certain threshold of energy, it's going to happen. If I turn up the intensity of that light source, what I'm going to be doing is generating more and more photons, but not necessarily giving more energy to individual photons. All right, yeah, let's just move on and take a look at how this, look at some diagrams here. So what would happen is this. Now, usually when this is done, rather than thinking in terms of the energy of the photon, we're thinking in terms of wavelength. So if we start with wavelength and then convert that into frequencies, we can plot frequency of light, knowing that the frequency is directly determined by the energy of those photons. Now, for very low energy photons, nothing happens because there's a binding energy of the electrons in the material. But once we cross a threshold energy, we begin to see that the electrons are being produced, and they're being produced with more and more energy. So here we are shining the light source in. If the photons in that light source are really low energy, nothing's going to happen. I mean, they're going to be absorbed by the metal or they'll reflect off. We have to cross a threshold, and past that threshold, electrons will start to be pulled from the surface, and that will show up as a current in our circuit. So let's try an example. Here it says, calculate the electron energy. Now it says speed, so we'll do that too. What's the kinetic energy of an electron coming off the surface of sodium? Now, who starts with a block of sodium? That sounds like kind of a dangerous thing to work from here. But they're saying that the binding energy for sodium is 2.28 eV. Now, what we're going to do, this is a set value for the binding energy. What we're going to do is we're going to send in two different wavelengths of light. And as a result, they're going to have different energies to them, and find out which of these wavelengths of light are going to be able to produce a photoelectric effect. So here we go. Example 37.5, photoelectrons. Here is the block of sodium. Now you guys know sodium's reactive, right? So this can't be done in the air, certainly not if there's any water vapor around. But here's a piece of sodium. We're going to put it inside a vacuum tube. And inside the vacuum tube, there won't be anything for the sodium to react with. So we're going to be good. So this is sodium metal. Now, the energies of these photons coming in, they can be calculated using hc over lambda. And for the blue light, that's 3.02 eV. And for the green light, which they gave us, 550 nanometers, That worked out to be 2.25. So those blue photons have more energy than the green. Let's take a look at the binding energy. Now, physicists refer to this as the work function. I kind of like the chemistry approach of just calling this a binding energy for the electron. So the binding energy of the electron, 2.28. Our green photons are not going to have enough energy. So we will not see a photoelectric effect from the green photons that had a wavelength of 550. Well, what about our blue photons? The blue photons are going to be able to produce this effect. The blue photons have more energy. That's going to be able to overcome the work function of the sodium metal. So what we can do is take the energy of the photon coming in, subtract off the energy required to separate the electron, and find out how much energy is left. That will be the kinetic energy of the electron. So in our example, that's 3.02 eV, subtracting off 2.28 eV, and that leaves 0.74 eV of kinetic energy for the electron. Now, we just did a chapter on relativity, so I wanted to try out a relativity formula for that. In the relativity chapter, we learned that the gamma value for the electron would be 1 plus kinetic energy over mc squared, where the electron mc squared is 511,000 eV. I got a gamma factor of 1.000001448. You know what? This electron doesn't necessarily require us using relativity, but why not? Relativity is not going to get the answer wrong as long as my calculator is keeping enough digits to make this number meaningful, and it is. My calculator is keeping 10 digits of precision. So this number works as a gamma, and then I can solve V from there. So just a little going back to the previous chapter, and there's a factor of C there that got left out. So get a factor of C put back in there. It worked out to be 0.0017 times C. So it's moving 0.17% of C. I didn't put it in meters per second. I guess I should have put it in meters per second too, but that's the approach. So these photoelectric effect problems, I want to say, are pretty straightforward. If we compare that with the thermal radiation formulas, this seems more straightforward, right? All right, so let me move on from this. So here is an example of the photoelectric effect for light. Let's go move ahead a bit here and talk a little bit more about some other properties of these photons. So this is related to the light bulb example that we saw before. Here they want us to calculate photon momentum and force. It says go back to that light bulb example where you had 10 to the 19 photons every second, and now we're going to focus that on a piece of black paper, and that black paper is going to absorb all of it. We want to calculate how much momentum each photon has and what's the force of all the photons. So let's go back just to remember that problem. What it said was that we had a 3-watt light source, and that each photon we were imagining had an energy of 2.50. That puts it kind of in the middle of visible light. That's going to be like, you know, yellow or green light. So there is the energy. There's the energy in terms of joules. Now, the momentum, if you remember, we wrote down those formulas from special relativity. The momentum, PC, is equal to the energy. So I can just say that PC is that 4 times 10 to the minus 19 joules. Now, I went back and dropped the factor of C. And that turned into, when I dropped the factor of C, my momentum of the individual photon worked out to be 1.33, 10 to the minus 27 kilograms meters per second. So 10 to the minus 27, that's not very impressive, but hey, it's just one photon, right? It's not going to have a lot of momentum to it. Now to calculate the force, we got the momentum calculated. What we want to do is say that the force is the rate at which momentum is being transferred, or the rate of absorption of momentum. Now I got this black piece of paper and I got all these photons shining on my black piece of paper. To keep the problem simple, they're assuming that all the photons get absorbed, and that means all of their collective momentum will be absorbed by that piece of paper. How much force is that going to be? Have you guys ever tried shining a light on a piece of paper to see if it, exerts a dramatic force on the piece of paper? So to calculate that, that's one way that we've learned to calculate force, is momentum transfer rate. Now, we could go with that. I guess we could have really used this right then, huh? Instead, what I did is I used this expression and converted it into energy and said the force is equal to 1 over c times the power. Now, the power seemed easier to me, I guess, because we already had the collective power. The combined power of all those photons is 3 watts. So again, we could have done the individual momentum and then multiplied. How many photons did we have here? Oh, that was back on that other problem. It was like 10 to the 19th, almost. It was like 7.5 10 to the 18th, 10 to the minus, or 10 to the 18th photons. We don't need that because this is including all the photons now. And I put that in for power and divided it, and I got 10 nanonewtons. You know what a nanonewton is? It's a billionth of a newton, and a newton is not a lot of force. So a newton is kind of a very gentle push on something. Nanonewtons, it's not going to blast that piece of paper. You're going to need a more powerful light bulb if you're going to want to blast the piece of paper off in some direction. All right, here is another example with photon energies. This one involves photosynthesis, one of my favorite biomolecular processes. What it says here is that photosynthesis in plants is able to convert carbon dioxide into carbohydrates. Now it says here that we need about 9 photons to convert a carbon dioxide to a carbohydrate and then release oxygen. Now it says that the light that the plants are using is 670 nanometers, so it's looking at the absorption in the red end of the spectrum. Now if I remember right, there's like 2 different photosynthetic systems, right? Some that absorb in the red. Aren't there some others that absorb in the blue? I need to go back and double check that. Anyway, that was always, I thought, the reason that leaves are green is because the plants are absorbing the red light and the blue light, but they're reflecting away the green light. They're not using it. Anyway, so it is showing where the chlorophyll most strongly absorbs the light, and it's asking for efficiency. So let's try this one. Again, this is one of my favorite, this is a favorite chemical reaction of mine. It's producing sugar. So we're going to take CO2 from the air, and the plant is going to take H2O from probably its root system. And it's going to run a bunch of chemical reactions. Now it's going to bring in 54 photons. Now I got that number, I hope it's the right one. It says it takes about 9 photons for 1 molecule of CO2. So now if I'm forming glucose, which is, did I mention that's one of my favorite molecules? If I take 6 carbon dioxide, I'm going to need 6 carbon dioxides to do that. So 6 times 9 was 54 photons. So I'm thinking when I create glucose, I'm going to be requiring 54 photons hit the photosynthetic centers in those leaves. It's going to have to hit that chlorophyll. Now, it claims that the wavelength that the photons are taking in of light is 670 nanometers, and of course I immediately change that to energy because that's the important property. In all these calculations, first thing we do is convert into photon energies so we can start looking at energy calculations. It turns out that these photons coming in that are being absorbed are bringing in 1.85 eV. Now, if I'm using 54 photons to generate my glucose, that is 100 eV of energy. Yeah, that really worked, huh? So that's how much light energy I have to bring in. I have to bring in 54 of those photons, and it adds up to be 100 eV of energy that comes in. Now, every time a glucose undergoes a reaction, the reverse chemical reaction releases 4.9 eV per molecule. Again, they're doing it in terms of CO2, so I had to boost that up. And I think I should have boosted it up by a factor of 6. So what I'm thinking right here is we might need to change a number on this. Yeah, I think if it's every molecule of... Yeah, I think this time that needs to be a 6 instead of a 9. So this is going to be scaled down by 2/3. That's going to put us down at 30%. So I apologize for that. That should be a 6. I'm thinking that would give us somewhere around 30 EV, and 30, I can do that. 30 EV compared with 100, it's going to be more like 30% of the energy was stored in the glucose. So the glucose was able to take 100 EV, or the plant was able to take 100 EV of energy in photons and store up 30 EV or so as chemical potential energy in glucose, which is one of my favorite molecules. Okay, that actually is a good place to stop. So let's stick with just the photosynthesis example, and we'll pick up with the rest of chapter 17 next time around.